Hello everyone, this is Chao Jizhuo. I am from Rutgers University. Today I will present our paper ArcGraph, All-Range Approximate K-nearness neighbor graph. Nowadays, with the development of machine learning models, we can embed everything. We can transfer images, documents, graphs to some high-dimensional dense vector. But in the real world, the objects are not just vectors, but also contain some structured key attributes. For example, some search key. In this example, the vector generated by the monitor will contain a search key as the timestamp. And this is another example. The voucher on the e-commercial website will have a search key as their price. With this vector embedding, we can build a K-nearness neighbor graph, which is a directed graph that each node connects to its K-nearest neighbor. And we will have a similarity measurement to measure the distance in relationship between the nodes. For example, the Euclidean distance for the high-dimensional vector. And this kind of graph have a widely application like high-dimensional data visualization or semantic searching. But the problem is that calculate exact KN graph is expensive, which needs at least n-squared calculation. So the researchers proposed approximate K-nearness neighbor graph, K-graph for short, in 2011, which will calculate the approximate K-nearness neighbor. And with this great NNDCN algorithm, we can achieve a high recall in a short time. And in our work, we focus on the problem to obtain K-graphs among the arbitrary search key ranges. So if we just simply apply the naive NNDCN algorithm, we need to build n-squared graphs online. And how about decide an index to storing all the n-squared graphs in advance? So we propose the ArcGraph, which is all-range approximate K-nearness neighbor graph. Here is the formalized problem definition. We will be given a vector set D, and each vector in the vector set will have a search key value I, which is a numerical value. For example, here we have 20 vertices, and each vertex have a digit represented their search key value. And the query will be a range xy, which is in the same domain of the search key value. And we will also give the K for the K-graph's neighbor size. And the output is a K-graph over the subset that each vertex in the subset has a search key value that larger than X and smaller than Y. For example, here we can have a query that range from 4 to 13, and our K is 2. Then the target output is a 2NN K-graph over the vertex from V4 to V13. The challenge here is that a naive index using the NDCN need to store the n-squared K-graphs for all the possible ranges, which means the index size is large, and the index time is also large. So we propose the ArcGraph to solve these challenges. And with our approach, we can reduce the index size from OKQ to OKN log n. And our index can be built efficiently with a small overhead based on the NDCN algorithms over the whole vector set, because we propose a closed model to avoid sorting all the pairs of vectors. Finally, with our ArcGraph index, we can answer the range filtering K-graph query directly. Here we start from some observation. In the most naive method, we need to store all the neighbors information for every combination of the range. But actually here we can see these three ranges sharing the same neighbor list. So we can compact them together, and we call this as the compact ranges. Here is the formalized definition of the compact ranges. It will consist of two intervals, B and E. And all ranges starting from B and ending with E will share the same adjacent list. And we make sure this B and E is the maximum, which means they cannot expand anymore. And we have a guarantee that using just Kn compact ranges can represent all the n-square ranges for each data vector, because there exists a subtraction relationship between the ranges and the compact ranges. And now the total index size will be k square n square. Besides, we found that actually we can separate the whole vector set to left part and right part using the position of the indexing point. For example, here we can separate the vertex from 1 to 6 to left part and from 7 to 11 to the right part. And we can record the two nearest neighbor in the left side and also in the right side. Then finally, when we need the whole nearest neighbor among all the ranges, we can just simply do the merge sort. And we call this technique as the partial ranges. With the partial ranges, we can split the original compact ranges to left side and right side and store the nearest neighbor separately. And now the index size will become Kn squared. Besides, we have another observation that the two adjacent ranges will share many same neighbors. For example, here we can see the R3 appears in the ranges 1, 2, and also appears in the ranges 3, 3. Actually, the two adjacent ranges will just differ at one neighbor. So we can apply the delta compressions on our partial ranges. And in this way, we can further reduce the index size to On squared. Here is a summary about the index size and the expected batching time for our former technique. And all the former complexity actually are the worst case complexity. But in the real world, if the vectors are distributed randomly in the vector space, which is the most usual scenario, the expected index size is much smaller. For example, for the compact partial ranges with the delta compression, we can reach a index size as OKn log n. Another problem is how to construct such index. Suppose here we have 11 vertices and we have all the distance information between the vertex 6 and the other vertex. We can solve from the nearest to farthest by the distance. And we will produce the left side and right side separately. And the initialize is the two nearest neighbor, V2 and V3. Then we will visit all the other vertices one by one and compare with the leftmost elements by position. For example, here, when we meet V4, we found that its position 4 is larger than 2, so we will pop out the vertex 2. And when we meet vertex 5, also, we will pop out vertex 3. Finally, when we meet vertex 1, because its position 1 is smaller than 4, we will just skip out this vertex. And here we can get a complete path of the arc graph index. In the same way, we can apply this to the right side vertex. And to efficiently sort all the vector, we can use the NDSet. Suppose we have a 5NN K-graph and as the yellow vertex. We can use this information to skip out some vertex because we know that these two vertex is the are the most nearest one to Vi. So we don't need to sort these two blue one. But still, we have a large number of the vertices need to be sorted. So we can use the two hop labels here. Suppose the white node here represent the two hop neighbors of Vi. Then with the help of two hops neighbors, we can skip more neighbors now. And we propose a cost model to decide the number of hops and find most efficiently hops for each vector. Now comes to our experiment. We evaluate our methods on two datasets, and we use the accuracy and query latencies to evaluate our result. And we implement three methods. The compact graph represents the compact ranges. The arc graph represents the partial ranges, and the arc graph data represent the partial ranges with the data compression optimization. Here is the experiment of the construction time. We can see that the arc graph have a much smaller index size comparing to the compact graph, because the arc graph will have a smaller number of the compact of the JSON list. Also, it has a much smaller index time. And in this experiment, we evaluate the efficiency of our cost model. We can see that with our cost model, we can always find the best number of hops for efficiently sorting. And we can boost the index time at least 5 times. And here we evaluate the data compressions efficiencies. Here we have two different indexes to store the data information. One is using the segment tree, another one is just record addition. And we can see the index time are similar for all the four methods, because the sorting time will dominate the whole indexing part. And we can see the arc graph data and arc graph data row have a small index size comparing to the arc graph. The arc graph data with the segment tree have a larger index size because they have some overhead to store the tree structure. And for the query processing, we can see that with our arc graph, we can answer the query within just 1 second, comparing to the original NDSend, which our method is 1,000 times faster. What's more, we can keep a high accuracy for the arc graph structure. We can see that in our methods, we can reach a recall larger than 0.95. Here is the scalability experiment that we change the dataset size and compare the index time and index size. We can see that our methods will grow linearly with the increase of the dataset size. So it has a great scalability. Also, we evaluate the query performance by changing the dataset size. You can see even with increase the dataset size, we can still answer the range query very efficiently. And also we can have a very high recall. So here comes to our conclusion. In this work, we studied the orange approximate k-nearest neighbor problem, and we propose an efficient index structure to compact the arc graph. And we decided efficient indexing algorithms to build the index. And with our index, we can restore the k-graph in any subrange instantly. That's all. Thank you.